And today what we will do is we will talk about gears primarily. So I'm assuming everybody knows about gears. So what we will do is today we'll talk about gears, and these gears primarily what we'll discuss would be types of gears, and then there would be some of the nomenclature, some of the key concepts about gears, and then we'll also talk about some of the basic gear concepts, how gearing actions take place, and then talk about gear trends and solve a simple problem. So before we start with gears, let me show you a small video of what gear exactly is and how it evolved. It's a very interesting piece of video. I enjoy it. So let me do that. And
meet Mr. Archimedes of ancient Greece. Long ago, Archimedes said, "Give me a lever long enough, and I can move the world." What Archimedes meant was that the power of a lever is practically unlimited. Today, almost everyone uses some form of lever in his daily work. The familiar can opener is a lever with a sharp cutting edge. The playground seesaw is just a simple lever, too. It takes a lot of force to start a freight car moving, yet the railroad man can start the heaviest freight cars easily with a pinch bar, a powerful lever which turns the wheel. Tough luck, old boy. Here's a place where a lever comes in mighty handy. Let's take the simplest kind of lever, a rigid bar working on a fixed support called a fulcrum. One end of this lever is twice as long as the other. Let's put a 10-pound weight on this end, and now we'll put half as much weight on this end. 5 pounds, balance 10. If we have 25 pounds to lift, we just use a longer lever. The 5 pounds will now balance 5 times as much. There, change its shape a little, and we have a crank. Or we can add a second lever and have a double crank. Now the short arm moves 1/4 the distance, but we get 4 times the force. If we want continuous motion, we need more arms. Now we have levers that turn. The larger paddle wheel makes fewer turns, but it delivers more force. A paddle wheel is nothing but a never-ending series of levers. We can make the wheels stronger and lessen friction where the wheels touch each other by rounding off the edges and shaping them into teeth that will slide in and out smoothly. Now, the power flows smoothly and continuously through spinning leverage of gear wheels. Gears are made in many kinds and many sizes. Little gears, big gears, worm gears, bevel gears, and even lopsided gears. Over 100 million gears are spinning over the roads in the transmissions of our automobiles. The transmission is located right at the bottom of the gear shift lever. Let's start from scratch and put together a model of the gears that we shift in our motor car. The shaft on the left comes from the engine. The shaft on the right carries the power back to the rear wheels. To connect these two with gears, we'll need another shaft, known as a counter shaft. These two gears carry the power from the engine shaft to the counter shaft and are always connected or in mesh. This gear on the drive shaft going to the wheels is free to turn around the shaft. We'll put it in mesh with another gear on the counter shaft. These gears are always in mesh. And keep turning while the engine is running. To switch from one set of gears to another, our transmission needs a short shaft like this, known as a clutch sleeve. It cannot turn on the drive shaft, but it is free to slide back and forth. On the sleeve, we'll mount a large gear, which we can shift back and forth to mesh with the small gear in the middle of the counter shaft. We are now in neutral. The gears that are always in mesh are turning over with the engine, but the shaft to the rear wheels is standing still. A 3,000-pound automobile takes a lot of force to start. So in low speed, we get the greatest leverage by letting the smallest gear on the counter shaft turn the largest gear on the drive shaft. The engine on this model is running at a constant speed of 90 revolutions a minute. With low gears in mesh, the rear wheel is turning at 30 revolutions a minute, about a third the speed of the engine, but with 3 times the force. The power is going through these gears in the transmission. After we've started the car rolling, we want fast pickup. So we shift into second by sliding the sleeve backward to mesh with this gear on the shaft to the rear wheels. The wheel is now turning at 60 revolutions a minute, and the power flows through these gears. For higher speeds, we let the power go directly to the rear wheels. We shift the sleeve forward so that it meshes with the shaft from the engine. The power travels straight from the engine to the drive shaft. Now the shaft to the wheels is turning at 90 revolutions a minute, the same speed as the engine. But here's a problem. An automobile must be able to go backward as well as forward. So we add one more set of gears to reverse the shaft to the rear wheels. With the gears shifted into reverse, the power travels through the transmission in a path like this. We now have 3 sets of spinning levers for going forward and 1 for reverse. With a gear shift lever, we can shift to any set of gears we wish. But with all these spinning levers in the transmission came noise and wear. Experts could shift gears quietly by careful timing of the gear shift and the engine speeds, but most of us made plenty of noise until new engineering developments made possible a long series of improvements that followed. When we shifted gears, we got a clash because the gears were not running at the same speed. In other words, not synchronized. So engineers set to work to develop a synchronizer. The synchronizer works like a cork twisted into the top of a bottle. The cork will turn until it is so tight that the bottle turns with it. Synchro mesh works the same way. When we shift into second or high, the synchronizer brings the gears to the same speed before they come together. The drums won't let the gears shift unless they are turning at the same speed. When the gears come together, there is no clash, and the shift is made quietly and easily. In the transmission of the up-to-date automobile, we have a powerful low gear to give us a strong spinning leverage in starting. A fast-turning motor must set the weight of the car in motion. In second speed, we can change leverage to get going fast at the same engine speed. With the leverage of third gear, power goes directly to the rear wheels, and we can go as fast as we want. Now, every driver can shift gears at any time, regardless of speed. Here is a hill that will give us a real chance to see how smoothly and reliably our spinning levers work in our automobile transmission. This driver is going to let her car gain a speed of 60 miles an hour down the hill. Then she will shift into second speed and bring her car easily and safely under control before it reaches the bottom of the hill.
So we'll stop here. I think let me go ahead and now unshare this and share this screen. 1 second. Okay. So now pretty much all of you know what how these gears work, right? So let me just go ahead and so basic use of gear, you understand that yeah. So this is what we'll cover today. First will be type of gear. Sorry. First will be type of gear. We'll discuss what types of gears are available: spur gear, bevel gear, worm gear. Some of it was described today in that small video which we saw. And then also there are helical gears and other sorts of gears also. So there is a whole list of gears. And then we'll basically talk about some of the nomenclature, some of the key nomenclature actually. So the key nomenclature you will talk about. The key nomenclature would be what is pitch circle, what is module, and what is pressure angle. So there are certain requirements which specify a gear, right? To basically uniquely specify a gear, there would be some parameters which will be required, and we'll talk about what parameters would be required. So that's something which we'll discuss. And some basic gearing concepts which are pretty simple we'll talk about, and some gear trains which is also very simple. So that's what we plan, and we'll solve a small problem. So basically functions of gear is primarily power transfer. Typically what happens is I have motors, right? I have motors or some prime mover, right? Motors and prime movers. So motor, it can be an electric motor, it can be a turbine, right? So these things drive certain things, right? And typically what happens is I would need different level of torque. Sometimes I need high speed, low torque, and other conditions. So typically when I'm starting out, I would need I'll be at low speed and the torque would be very high. Torque requirement is very high. So I would need a mechanism to basically able to change this speed and torque, right? And some cases we want to have constant speed ratio. So for all these, we would need some sort of a mechanism which can basically change the rotational speed and torque and transmit the power. And that's what gear does. I'm assuming everybody has, at least I don't know, because this time you are not able to do it, but gears will be a portion of your KDOM class. So you'd probably know a little bit about gear. Maybe this time it was not covered as you guys told me, but I would expect you would know a little bit about gears. So basically what happens is there is something called pinion, which is smaller gear. And then there is a gear, which is the output shaft, which is mounted on the output shaft. So there is pinion and a gear, and it gives some power, some rotational speed, some torque, and it spits out output power, omega out and T out. Mostly your power will be with some losses, minimal losses, but power would be conserved. So what goes out would be your basically, if you'd like to think, your omega changes and torque changes. That's pretty much what happens. Your rotational speed will change and torque will change. Speed will change and torque will change. So that's what happens. Right. Now there are different kinds of gears. What I will do is I'll show you some of the gears. So the simplest of all gears are, if you would like to see, simplest of all gears are something like this. These are called spur gears. So this is one thing which is driving, and then there is one which is driven. So typically what happens is if you want to provide higher torque, you would use a larger wheel so that you get higher torque and lower speed. So speed reduction and torque amplification. So this would be a simple spur gear kind of a thing. Now, there are other things. There are helical gears also. So this is one example of a helical gear, if you'd like to see. This is a helical gear. So this is not a straight thing. The teeth are around a helix, right? And then there would be there can be worm and worm bevel gears. All sorts of gears are there. So I can also show you some sort of a worm gear mechanism. So this would be something like this, So there will be worm gear, and what this can do is this can if you move that, you will get some sort of a linear motion kind of. And then is rack and pinion also, right? So you have worm gear. So worm gear, what it does is if you rotate, it can move, right? It can engage in this direction. And then rack and pinion also provides rotary motion to linear motion. So there what will be, there will be a rack and there will be a pinion. I don't see it here, but rack and pinion also is one arrangement. And then you will have planetary gear systems where you can have multiple gears and then an internal gear. So this is a planetary gear system. And then you can also have hypoid gear, right? So these are the kind of gears. Bevel gears, typically what they do is they do 90-degree transmission. So what will happen is there would be one. I don't have a bevel gear here, unfortunately. I don't have it, so I'm not going to show it. But it was something like this. So they have these tapered things. So one is at 90 degree to the other. You saw that in the video. So taper. So basically, it will transmit power at an angle. So that's what bevel gears do. At 90-degree angles, you can transmit power. Okay. So this is what we talk about a little bit, and then there is a gearbox which you saw in the video how gearbox works. So basically, for transmission of power, if you have to have different speeds, different torques, so you can have switching between the gears. So you can have multiple options to do gears. So a classic gearbox is what you have in your automobile, right? Start from first gear, you have high torque. Then as you increase the speeds, we don't require that kind of a torque, right? So you will shift to higher gears. So that would be, this entire arrangement is done in a gearbox. So types of gear I showed you is spur gear, helical gear, worm gear, and bevel gear. So these are types of the gears which will come across. There is another unique concept which I would like to kind of describe. There is something called line of action. So this line of action is very interesting. What happens is the power transmission has an angle. So this angle actually what it does is at the point of contact, if you see pitch circle diameter, these are two pitch circle diameters, and then there would be a base diameter. So there is a pitch circle. I'll describe what all these means. Pitch circle. So pitch circle basically means there's an imaginary circle in the gear at the point of contact. Imaginary circle at the point of contact. So both the mating gears would have their respective pitch circle diameters, right? So this is what it is, and then this is the base. The bottom one would be the base, and the pitch. Basically, the mating happens at an intermediate location. So this is the another tooth, this is another tooth, the two tooth. These two teeth will meet here, and the mating point of these two teeth, there is an imaginary circle. If you draw from both the center of the shafts, you would see two circles. This will be pitch circle diameter for this gear and PCD for this gear. Now the funny part is the line of action, the way it works is it's actually at the tangent of the base radius. So it passes through this line of action, it passes through the point of contact, but it makes a tangent with both the base circles, RB1 and RB2. So it's tangent to both the circles. So if you can imagine, what will happen is this is from the vertical to this will be 90 degree. So this is called phi. So if you look at this is 90 degree. This would be phi. This would be phi. So this phi is called pressure angle. Pressure angle. Pressure angle. And this is the angle which the base radius. So base radius is always tangent to both the both the circles, right? Both the base circles. This line of action passes through both the base circles, and it is a tangent. It's tangent to both the base circles, and the angle between the vertical and wherever this contact at the base circle is phi. So can you understand what I mean by this line of action, or is there a doubt? If there is a doubt, just let me know so we can discuss a bit more.
Excuse me, sir.
Yeah, go ahead.
Sir, does the line of action depend on the geometry of the teeth?
Yes. It's a geometric parameter. So line of action actually basically the pressure angle which the line of action decides is actually a gear parameter. Phi is a gear parameter. So typically it's 20 degrees or 25 degrees. That's what the gear is designed to have a fixed pressure angle.
Sir, does it depend on the teeth structure, like cross section, how the teeth
No.
look?
So the teeth are designed like that. The teeth will have an involute profile, and the teeth, the way they are designed, is that you will always get these point of contact, right? Will always make. So the way the teeth are designed, the inward profile is designed, you will get a fixed phi. So a gear is designed for a given phi line of action.
Okay, sir. I got it.
You can change it. You can make it 14 degree. You can make 20 degree, 25 degree. But that's a geometric parameter. It will be a function of how your tooth form is there. How does the tooth form is there? I'll show you the tooth form in a little bit. So a tooth has a distinct form, which is called an involute profile.
Okay, sir. I got it. Thank you.
We'll show you a little bit more. So basically, when the gear tooth profiles are designed so that they produce a constant angular velocity ratio during meshing. So there is something called a conjugate action that has to happen. Conjugate action, because they have to mesh. So when they have to mesh smoothly, you need a profile in the tooth, and this profile is nothing but an involute profile. Of the tooth has an involute profile, and this involute is made if you basically take something like you unroll. So basically, if you take I would say a roll of thread, right, and unroll it keeping taut. Unroll it keeping taut, so it's always a tangent. If you keep it unrolling it, the shape which it will make is involute. So keep the wire taut and keep on unrolling it. So the trajectory which it will make is nothing but involute. So that is the trajectory you want to have this conjugate action. The conjugate action always gives, so your profile of the tooth would be something like this, and this profile is involute, which is a trajectory you get when you basically keep on unwrapping a tangent cord from the base circle. So it's always perpendicular. Tangent is always perpendicular, right? But you keep on increasing the length. So it basically just like unwrapping the thing. So you will get a involute profile, and that profile is very important for gearing action. Otherwise, you'll not get smooth meshing. Okay. So what will happen is we'll always get, there will be no slipping, right? So it's pure rolling. So we'll get R1 omega 1 is equal to R2 omega 2. This R1 and R2s are pitch circle. This R1 is equal to R2 is equal to pitch circle, and omega 1 is nothing but the rotational speed, which is function of RPM, right? So this is what gearing action is. Now this is something very important I want to show you. This is how a gear teeth looks like. So this this you see, right? This profile is involute. And the pitch circle is this. The pitch circle is this. Sorry. The pitch circle is this. This is the pitch circle. This is where the contact will happen, right here between the other tooth. So this is where the contact will happen, right at the pitch circle between the mating tooth and the with the two mating teeth, right? So pitch circle, and whatever of the gear portion which is above the pitch circle from the top of the top land, which is called the top of the gear, that's called addendum. Addendum. Whatever is at the bottom is called dedendum. Dedendum. And addendum will be total height of the tooth. Now, can somebody tell me which one will be bigger, addendum or dedendum, and why? I need an answer. Which one will be larger, addendum or dedendum? Why would addendum be larger? It's a correct answer, but now tell me, why is addendum larger? The teeth can't mesh. Can it be equal? Can it be equal? Yes or no? So you always need the clearance between the mating tooth, right? So if it is less, it will not go through, because there will be interference. If it is just equal, still there's a chance of being some interference, some rubbing. So you want the clearance between the two teeth. So you want the dedendum to be slightly larger than the addendum, right? So that way what will happen is your dedendum has the mating tooth also would have some geometry, right? So we want some clearance. So clearance will always be dedendum minus addendum. Dedendum minus addendum. Any questions about the geometry of the gear? Any questions about the geometry of the gear? Do you have any questions about this geometry of the gear? If not, we'll move on to something else. You can imagine. So this is an involute profile to make sure it always rolls. Wherever it contacts, it always rolls. So there is no. It's called, what is it called? There is a name for this, right? We call it conjugate action, where there is no slipping. Right. Now I will go through some definitions. It is the position of pitch or dependent on the other mating gears. So I'll tell you what are the key features of the gear. So pitch circle, both the gears will have similar involute profile. So basically, when you define a gear, so these are the things which you need to have. Something called, it's called diametral pitch. So diametral pitch is basically N over D. N is number of teeth. N is number of teeth. Number of teeth. So the first thing, if you go and you want to talk about gear, there's something called diametral pitch. This diametral pitch is nothing but N over D. And people typically in the gear parlance, they use something called module of a gear. Gear module, which you would probably in the metrology class, you did not, you guys would have done that mostly, measured the module of the gear. I'm sure you'd have done that in the metrology lab. Yes, you would have done it, right? You are in final year, right? So metrology is in third year. So you've done the metrology lab, I believe. So you measured the module of the gear, I believe. Right. So the module is just inverse of diametral pitch. 1 over diametral pitch. which is basically d over n. So your question is that, is the position of pitch circle also dependent on the mating gear? The answer is yes. But what happens is your pitch circle diameters typically are designed for a gear. So every gear has a pitch circle. So contact point of the gear is known. So pitch circle is not dependent on other mating gear. Pitch circle is the property of its property of the gear itself. So whatever gear you buy, right, it has a pitch circle diameter. So it doesn't really depend upon the mating circle. But what will happen is both the gears, right, will actually mesh at their pitch circles. Get me? It's not dependent on the other gear, but it is a property of the gear itself. So the mating point of a gear is fixed. If you would go ahead and see, the mating point of the gear is fixed right here. So this is the point where it will mesh with other circles. So it's actually it's by geometry defined that this is how this this will be, because the reason is that we know that the base circle, and this is, so base circle is RB cos phi. So the base circle is defined, your pitch circle and your base circles are both fixed. And so phi is defined, your RB is defined, and pitch also is defined. You get me? So these are pitch, phi. If it is defined, then your basically your where the circle will meet is actually designed in the gear itself. So pitch circle is a gear property. It doesn't depend upon the other one. So basically, if you see, diametral pitch is n by d. Module is something which typically problem solving, I'll talk about diametral pitch. But if you go to a shop to buy gears, they will talk about gear module. So module is what the gear manufacturer will show you. Then there is circular pitch. Circular pitch is pi m, pi times module. Then there is base pitch. Base pitch, PB, is pi m cos phi. And your base radius, remember, your base radius is your actual pitch radius times cos phi. This also you have to remember. Okay. And typically addendum is m. And addendum can vary 1.157, 1.250, 1.4, so depending upon what clearance you require. Do you require large clearance? You require small clearance. You can choose the addendum. Right. And you need these three parameters, m or p, both are same things, n, number of teeth, and phi. So uniquely, if you want to characterize a gear, if you want to identify a gear, go buy a gear, right? You need to tell them the module or the pitch, diametral pitch, number of teeth, and pressure angle. If you specify m, n, and phi, you have a unique gear. You can go ahead and buy it. Okay. Right. And then common pressure angles are 20 degree and 25 degree. This is what you will get in the market today. In olden times, they used 14.5 degree. Now they use 20 and 20, mostly 20 degree or 25 degree. And the face width is a function of small p, which is your circular pitch. So basically it is your f is between 3p to 5p. Between 3p to 5p, your face width. Right? So fundamental law of gearing is the common normal of the tooth profiles at all points within the mesh always passes through a fixed point on the line, and this is called the pitch point. So pitch point is the contact point. And this, basically the common normal of the tooth profiles at all points should pass through the pitch point, and the gear set velocity ratio will be constant throughout the mesh and equal to the ratio of gear radii. So this is what fundamental law of gearing is, which says nothing but says that number of So basically Ng by Np, number of teeth in pinion is the small one, number of teeth in the gear is Ng, is nothing but R by R. Right. So basically your this is what it says. So of course what will happen is R is so basically your N, so basically what you will get is your number of teeth and this are in the same ratio, right? Larger the number of teeth, the larger the R, which actually is common sense, right? More number of larger diameter means larger number of teeth. And then this will actually go ahead and this will be in the same ratio. So basically this is what is important. So basically your R2 by R1 is equal to N2 by N1, N2 and N1. N2 and N1 is basically number of, if you look at its number of teeth, right? So basically your omega 1 and omega 2. So you know that your there is no slipping, right? So linear velocity has to be same. So omega 1 R1 is equal to omega 2 R2. So basically omega 1 by omega 2 is equal to R2 by R1. And R2, if you want to just use, let me just use omega P, pinion and gear, or omega G by omega P, because driver is omega P. Omega G by omega P will be R P by RG, right? And this will be equal to number of teeth, if you want to see, N capital NP by NG. NP by NG. So what this says is your number of teeth on gear is larger. So basically, so if I transfer from small gear to large gear, I'll basically what I will do is I will have a lower RPM. Pinion is smaller, gear is larger, so you will slow the speed. So RPM of the pinion, your RP will be greater than, not NP will be, what is omega P is greater than omega G, because RG is greater than RP, because RG is greater than RP. Make sense? So the driving one, pinion is small, gear is big, so pinion can make more turns in gears. So gear will actually turn once and pinion will turn 5 times, right? So the RPM of the pinion will be higher than the RPM of gear, right? And then let's see the torque turn. So basically this is what is in terms of RPM. Omega is nothing but proportional to RPM, right? So we'll use revolutions per minute, which is what the engineers use. They don't use omega. Omega is only physicist thing. So we use revolutions per minute, which is proportional to omega. So basically I will say N3 by N2 will be equal to N2 by N3, or D2 by D3. This is what is for gear trains. So you can have multiple gear trains and you can use this same formula for that also. So if you have a lot of gear trains, so the way to remember would be is this E, basically NL times NF. So basically what happens is you can say there's a factor E, which is product of driving tooth and driven tooth. The same ratio you will get between N6 and N2. So basically what you have a gear train, some of them are driven, some of them are driving. So basically the ratio at the ends you will get is the product of the driving tooth numbers and the product of driven tooth numbers. You can work it sequentially and you'll get the same thing. Okay, so that's how the gear trains operate. Any questions here? Really simple. So you can just keep on doing 1 to 3, 3 to 4, 4 to 5. So basically the simpler thing is you just say product of driving, product of driven, and same ratio there would be this the final RPM, so you can compute. So the ratio of the driven RPM and the driving RPM, the end ones would be in the ratio of this all driving and all driven. Okay. So there is a practical limit on train value for one pair gears is 10 to 1. So if you want more, you'll have to use compound gears. Right. So basically, one pair of gear you cannot get less than 10 times reduction or magnification. Otherwise, you'll have to do multiple. So you'll have to have 2 gears on one shaft. Right. So that's where you can basically amplify more. So what happens is, say, if I have, say, a motor which goes at 3000 and I want 5000 or 20,000 RPM, right? 20,000 RPM. So what I will do is I will use gears to basically transfer the, so basically take 3000 and give it at 20,000. So I can have series of gears, sometimes more than one on one shaft, and get that magnification. So here I can actually get, so 10:1 I can get at 1, but more than 10:1 is not possible with just one set of gears. Okay, then you need a gear train. And these are compound gear trains. Again, same concept which I showed you. N5 by N1. N5 is at basically here. Here is the speed N5. Here is N1. Now what you have to do is you have to say minus N1 by N2, N3 by N4, N4 by N5, and you'll basically get what will be the gear ratios. Okay. So we'll do a small problem here. Let me just do a small problem. So what we are trying to do is we have a 16-tooth pinion and 40-tooth gear. The diametral pitch is 2. So let's go to the diametral pitch. The diametral pitch definition is what? If you go ahead, diametral pitch is nothing but N by D. Capital D is the pitch circle, pitch diameter. Okay, let me just go ahead and show you here. So I know P is equal to N by D, right? So what will be the diameters for, what will be the diameter of this 16-tooth pinion and 40-tooth gear? Can somebody tell me? So diameter is N by P. So diameter of pinion, let me use small d here, that will be easier. I'll just use small d here. So this is D. So my D pinion would be 16 by 2, 16 divided by 2, which is 8, right? And D gear is what? 40 divided by 2, 20. So this is 8 inches and this is 20 inches. D gear, right? Any questions here? So you understand, right? From my diametral pitch, I can find out, if I know number teeth, I can find out what will be the diameter, right? So these gears are cut using a pressure angle of 20 degrees. So we create these geometry of the gears which have pressure angle of 20 degrees. And the addendum is 1 over P and 1.25 over P. Addendum and addendum, right? So we have to compute the circular pitch, the center distance, and the radii of the base circles. These 3 things I have to calculate, right? So let's calculate the circular pitch. What is the circular pitch? Let me just go back and show you what circular pitch is. Circular pitch is pi m or pi by P, right? Circular pitch is circular pitch is pi by P. Right? What will circular pitch in this case? Pi by 2. So pi by 2 is the circular pitch. This is the first. Circular pitch is equal to pi by circular pitch is equal to pi by 2. Is equal to pi by 2. Now what will be the center distance? So between this gear and the other gear, what would be the center to center distance? Can somebody tell me? Anybody? What will be center to center distance here between these two? Very good. So it will be sum of the pitch circle radii, right? Here the pitch circle radii is 4 and here it is 10, right? 10. So 14 inches, right? And the base circle, radii of the base circle. How do I find the base circle radii? How do you find the base circle radii? Can somebody tell me? I talked about it in there, right? When we discussed it, I talked about it. How do you find the base circle? Yes. So you take the pitch circle radius and multiply it by cos phi, r cos phi, and you'll get it. Right? Now they tell you something very interesting. When you mount these gears, right, then what happened was these gears were mounted slightly erroneously, and this distance between center to center was 14.25 now. What happens now? Can somebody tell me? So these gears, instead of, they should ideally be 14, now they are 14.25. Will the pressure angle change? That's the first question. First question I'm asking is, will the pressure angle change now? Will the pressure angle change? Yes or no? Will it change? Somebody say yes or no. Will the pressure angle change or no? What you have done is it is supposed to be 14. Now you did some error when you are mounting it. It doesn't really done 14. You have made it slightly further because of misalignment or whatever. Your shafts were not aligned properly. Now the center to center distance has changed from 14 to 14.25. What will this do? So now what will happen is, first thing, let's go step by step. Do you think it will change the pressure angle? Yes or no? Anybody? It will not change the pressure angle. You sure? Let me get one step back. Will it change the pitch circles now? Yes, that's a very good point. Contact point will change. It's a very good thought. Now what I'm saying is, take a step back. Will the pitch circle now change? Now my center to center spacing has changed. Has the pitch circle changed? has the pitch circle changed or not? The moment you sure? You have misaligned it. Has the contact point changed or not if you misaligned it? Yes, right. Because now it was at 14. Ideally, you should have aligned it 14. But now what you have done is you have made a mistake. And now the distance between center to center has changed from 14 to 14.25. So now my mating is a different location now. Ideally, where it should have mated is not mating, right? So now what is happening is I have a new pitch circle, which is basically if I say dp dash plus dg dash by 2, right? Meaning rp dash plus rg dash, the new one. What will be this number? Initially rp plus rg, sorry, rp plus rg was 14. Now the new pitch circle rp dash plus rg dash is what? 14.25. Right? Yes or no? So my pitch circle has changed. So one equation would be that I can say that like this, dp dash new one plus dg dash by 2 is equal to 14.25. That should be the first condition. The second condition, what I'm trying to say is when it is mating, what will be the ratio of dp and dg? dp dash and dg dash ratio will be what? Will it change from the previous one? This ratio dp, the gear ratio, dp dg, does it change? Yes, it doesn't change because number of teeth still remain the same. So dp dash by dg dash will still be 16 per pinion, 40 for this. So you have two equations here. First equation, second equation. Now you can find out what will be the new dp dash and dg dash. Right? And then you can find out what will be the base circles again. Right? So we can find out what will be. So now you have new dp and dg dash. Base circle, does it remain? Does it change? No. So I can get that relationship from that. So basically, let me see. What I will say is basically I have dp dash dg dash is 14. So basically, let me go ahead and go here. So this is 14.25. This is 16. So I have dp dash and dg dash. Right now, what happens is my rb doesn't really change, but my dp dash has changed. So I can say that r cos phi is rb. So I can use my pinion rp. Sorry, my mistake. I can use the base circle of pinion and then find out what will be from the new r. I can find out what will be the cos phi, because I now have r dash, right? rp dash or dp dash by whatever we said that dp dash by 2, dp dash by 2. I can find out what rpv will be. Right? So this will give me the new phi, which is 22.56. So because of misalignment, the reason why I'm showing you this is because of misalignment, your pressure angle can change. Your pitch circle, so your pressure angle phi, and pitch circle changes. And pitch circle changes. Right? Right? So any questions you guys have? I think this was a short class, so not much to talk about, but if you have any questions, we can talk about it. Any questions, any concerns which you have? No?
Sir, about the project deadline. So, can we keep the presentations at 10th or 9th?
9th, it's difficult for me. I'm actually tied up with some very critical work. So 9th may be difficult for me. You guys want to do 10th? 10th is what day?
10th is let's check.
10th we can have 10th. So you tell me when you want to do it, and I'll be happy to do it on 10th.
10th is Thursday, sir.
No, 10th November, right? 10th November is
Oh,
Tuesday.
sir, not November. I'm talking about the final presentation.
Okay, when do you want to do it?
So 10th or 9th of December.
I have no issue, but when is the grades due? Because I would need to.
The grades is due on 13th, right?
Okay, so
As far
10th
as I
will work for me. If you want, 10th should be fine. I have no
Yeah.
issues on that one. But are people ready for 10th? You said that you have your these things, right?
Yeah, so that will be mostly in the first week of December, mostly. So accordingly, we are planning that let's keep it on 10th. Okay, so if anyone has issues, then please abhi bol do. Matlab.
So you run it by your class. If everybody is okay, nobody complains later, right? It will be, otherwise I'll have to to devote more time, right? You have to make more slots, which will become very messy. So I want to do it one go. Yeah.
Yeah, okay, so I asked in the WhatsApp group now. I think आप एक बार अगर mail डाल सकते हैं कि if anyone has any issues with 10, then they can mail on that. Because it might be possible that some people are not on the WhatsApp group or some people are not here in the class right now. So if you can put a mail, that would be good.
Okay, I'll do that. You just send me the dates, exact dates, and I'll do that. Not an issue. Okay. No, so there is, I think there's a question that is the base circle is pitch radius minus dedendum. No. Because what happens is there's an addendum circle, there's a dedendum circle, and the base circle is defined by basically RB cos phi. So R cos phi. RB is equal to R cos phi. There's a dedendum circle also. And there is a base circle also. Base circle is the circle where you can, if you imagine, the tangents meet. This is the base circle. If you want to understand base circle is this. Base circle is this. Base circle can be different than dedendum circle. Okay. There's a question about whether base circle I can get from pitch radius minus dedendum. The answer is that's a dedendum circle. That's not the base circle. Right? So base circle is always defined by wherever this meets. That's the base circle. So base circle definition is your pitch circle times cos phi is the base circle. Okay. And addendum dedendum are basically more like a gear manufacturing thing. You get me? So you make the gear will look like it. There will be addendum, there will be addendum, but base circle can be somewhere inside the gear also. Base circle and pitch circle. Pitch circle at least has a physical meaning, right? Because it's the diameter passing through the contact point. But base circle doesn't have that kind of physical meaning. Base circle is just the how you define your pressure angles. And pressure angle is actually a parameter which comes from your design. Okay. They may be very close though. Okay. Any other questions you guys have? So I would not give you any homeworks to grade now. I know you have enough work on your hand. So what I will do is I'll give you some practice problems. I encourage you to do it. I would not give you any more quizzes also. So the only thing now there would be your final exam. You should focus on your project now. So I'll not give you any additional load. I'll give you practice problems. I'll give you a final exam, and final exam will mostly cover 75% of the final exam would be the material which I have done after midsem, because I have not really tested you on that, right? I have not done any quizzes. I have not done any homeworks. So final exam will be skewed towards this new stuff. 75% would be new stuff, 25% will be old stuff. Okay, it's still cumulative, but 75-25. And that will be the only exam now you will have to take. I don't want to give you homework exams. I want you to focus on the project now. Okay. If you have any questions, shoot, or we can close this. I have some very pressing engagements actually. I haven't even had my lunch yet. So I'll try to answer questions if you have. Otherwise, I will have to take your leave. So can you have a module less than one? Okay, let me see how you define the module. So module is defined as d by n. So if your diameter is say 1 inch, can I have in a 1 inch diameter? Why can't I have 8? Let me see. So I have 8 tooth. Basically, you say that module less than 1 meaning what it means. Module is n by d, number of tooth by diameter. So number of tooth will always be more than 1. So if you say, I don't see, if you have why can't you make more number of teeth on a small diameter? Because this is a diametral thing, right? It is not a dimensionless thing. So ideally, even in 1 millimeter, you can make a number of tooth, right? So since it is a dimensional thing, I think you can have less than 1. I don't see why not. In a say diameter of 1 mm, you have like 5 teeth or 10 teeth on 1 mm diameter. You make really small teeth. You make a very micro gear. People make micro gears, so it's not dimensionally independent, right? So it can be. It can be because it's just a dimensional factor. So typically it will be basically pitch is d by n. So it is mm, 1 per mm. So basically it's per mm. So why it can be less than 1? So 1.5 teeth per mm. Why not? But these modules are actually available. These are standard parameters for gear. So you actually get when you look at the vendors, they will specify certain modules. Okay, so let me look in the book what standards people sell, what modules people sell. Okay, both for metric and the inch gears. Any other questions? So if not, I'll take your leave and shoot me an email about the project presentation. I am okay with any day. I have no issues on that one. I need a couple of days to basically consolidate the grades. But you do have to focus on. Yeah, go ahead. Yeah.
I think I was just saying okay.
Mm-hmm. So I just wanted to focus on the project because I'm giving you a lot of leeway. I haven't done any exams, nothing for complete half a semester. So I expect that you do good work. The only evaluation there will be of your projects in the second half of this. Okay, so I'm not overloading with you with a lot of other content because I want you to focus and put your energies in the project. Okay, so you better do a good job of it. Okay. So if there are any questions, shoot, or we'll meet in the next class. So if there are no questions, thank you so much for your time, and I'll take your leave now. We'll meet next Monday. Bye-bye.